Video, we're going to be looking at an equilibrium system for chemistry. This is particularly a graphing question, and yeah, let's just get pretty much straight into it. So an equilibrium system contains 5 molarity of nitrogen, 2 molarities of hydrogen, and 3 molarities of ammonia. So here they've put it in direct order with our equilibrium system here. So we have this, which is that, this, which is that, and this, which is that. Okay. Now, pretty much we have to construct a graph for our equilibrium system, and we're going to apply different scenarios to it to see how the concentration pretty much changes. Okay, so I'm just going to make this a little bit smaller, just move it there. So here, when it says construct a graph, we need to understand what we're comparing it to. So what we're doing is we're comparing the concentration, aka your molarity, with time itself. Okay, now here we've been given the molarity of each of these compounds at the start, pretty much, when t equals 0. So this is when t equals 0, okay? Now we also know this equilibrium system is exothermic because the delta H is negative, okay? Which will play an important role later. So, construct a graph for the following situations. The mixture is at equilibrium for 10 seconds. So pretty much here is we just draw the concentrations of each of these elements at their initial equilibrium for 10 seconds. So the lowest one being hydrogen. So this would be hydrogen, which is at 2 molar. This one here would be ammonia, which is at 3 molar. So we'll just go NH3, and then the nitrogen's the highest one, which is 5 molar. Now I'm probably going to make this graph a little bit bigger because of what's going to happen next potentially. I'll make this a bit smaller, and I'll extend just this line here. Oh, nearly. Just gotta be careful and just get that. Perfect. Okay. So here this is at t equals 10. So those are the concentrations at the start, assuming nothing else has happened to these guys here. So volumes are all the same. Oh, that's not hydrogen. That's hydrogen. And nothing else has been changed. Okay. So that first bit's pretty easy. The volume is halved. When the equilibrium system is re-established 10 seconds later, the concentration of the nitrogen is 9 molar. So pretty much here, with this system here, we're going to halve the volume. Now, if it was in terms of the Le-Chalais principle, it would shift to the side with the least number of particles for the density. But remember, this is molarity. Now, molarity is your moles over your volume, okay? Now, this is the initial molarity, okay, which that is the initial volume, now the moles aren't going to change because we're not adding any more hydrogen, ammonia, or nitrogen to this system. So the number of moles is constant. This is changing, and this indirectly changes due to the volume, okay? So what we have to do is pretty much label this. So this is initial. Well, let's just say this is constant. We'll just go initial. This is initial, and this is initial. Now, the new molarity, let's just go molarity, is going to be the initial moles, okay? So this is the initial moles over half the initial volume, okay? Now here, 1 over a half, which is what we have here directly, because we have 1 over a half, is the same as just rewriting 2, because 1 divided by a half is the same as 1 times by 2. So here, the new molarity is double the old molarity. So the new molarity is 2 times by the initial moles over the initial volume. Where if you were to think of it mathematically, we could just substitute this into there, and the new molarity is double it. So effectively, not applying Le-Chalais principle at all, if you halve the volume of this system here, or any system, it's going to double the molarity. So what's going to happen is the hydrogen is going to go to 4, so there'll be a spike here, and that will be at 4 molarity, and that's going to go, well, it will start to change eventually as well. So that's at 4 for the hydrogen. The ammonia is going to go up to 6, so that's going to spike up here to 6 molarity. So that's your ammonia. Let's just write that there. That's your hydrogen. I'll move it in a sec as well, because when we have to draw it. And the actual nitrogen is going to spike up to 10 molarity. Okay. Now, we've now made the actual system and we've established it. This is where the chemistry, or rather the mathematics, is going to come involved. Okay. So let's take a look at this. Okay. If I halve the volume, it's going to shift to the side with the least number of particles. Now here we have 4 particles on this side. We have 3 hydrogen to 1 nitrogen. And on this side we just have 2 ammonia. Yes, it's exothermic, but that doesn't count as a particle in this case here. Okay. So let's also take a look what's happening here. So if you increase the if you halve the volume, it will shift the side with least number of particles. So the ammonia should increase. Okay. So if the volume goes down, then the ammonia will go up. Okay. Which means if this is going up, that means the nitrogen and the hydrogen is going down. Okay. Now, so if I were to bring this down here, so the nitrogen is going down and so is the hydrogen, which makes sense because look here in the question. The volume is halved. When equilibrium is re-established 10 seconds later, the concentration of nitrogen is 9 molar. So the nitrogen decreased, which is exactly what we predicted. Okay. So now the nitrogen, so let's just write here, so the nitrogen is at 10 molar and it's gone down, let's say that's 9 molar there, it's gone down to here, okay? And that's 10 seconds later, okay? So this is T equals 20. So, if that's going down, this is going to go up, but we have to work out by how much it's going up. So this is where the ratios of our coefficients come involved. So let's look at this equation here. So nitrogen plus 3 hydrogen produces, what, 2 ammonia? Okay. So here, because it's shifting from left to right, it's going to subtract a quantity from the nitrogen. It's going to subtract 3 of that same quantity from the hydrogen, because they're ratios, because it's stoichiometry. And it's going to add 2 of that same quantity to the ammonia. Now, we know that the nitrogen went up to 10 molarity, and then after equilibrium went to 9 molarity, meaning the minus x here, it went from 10 to 9, that means x here must be 1. So it is minus 1 here. That means that's minus 3, and that's positive 2. So here, if we apply these numbers to the molarities after the volume has been halved, we can work out what their molarity is going to be after equilibrium. So here, that's gone down to 9 because that's the minus 1 in here. Now here which one? That's the ammonia. That's going to go up by 2. So that's going to go up to 8. So that'll be 8 molarities. So that's going to go up to there because it's getting plus 2 because it's increasing. And the hydrogen is going to go down to actually 1. Because it's going to go from 4 minus 3. Okay? Hopefully that makes sense. Now, I can also take a photo of what they have on the answer sheet here so you can also articulate as well if my working out isn't amazing. Okay? So let's just go here and we'll just take a photo of their stuff here without spoiling the next question. Give me one moment. I'm just going to take a photo of this document here. Okay, so hopefully you can see this now. So this is exactly what I'm talking about. So here it went up to 4 and then it went minus 3 all the way down to 1. Okay, the ammonia went up to 6 and then it increased by plus 2 to 8. And here the nitrogen we know went from 10 to 9. Okay, so it's important to have a good understanding of equilibrium as well as a bit of mathematics here with the molarity. Okay, so that's how you answer the first 2. Okay, alright, so let's move this whole thing down. Okay, so let's continue. We'll continue off their graph here because I think their graph is pretty good. And mine was getting a little bit messy. So let's go here. At 20 seconds, so this is 20 seconds, so this is 0, that's 10, That's 20. So at 20 seconds, the concentration of hydrogen is increased to 5 molarity. Okay. So here at the moment, oh, I think I didn't cut it. So yeah, again, it's increased to 5. It goes up to there. So it's at 5 molarity. When equilibrium is re-established 15 seconds later, the concentration of ammonia is 11. So let's take a look at this equation here. So N2 plus 3H2 ammonia. Okay, so if I've increased the hydrogen, Lechalle's principle basically says any change made to a system in equilibrium will oppose that change. So if I increase something, it wants to decrease it, okay? So because this has been added, it's going to decrease the hydrogen, which means it's going to decrease the nitrogen and increase the ammonia, okay? So basically, we can see here it's at 8 molarity. It's going to increase to 11. That's why it's increasing to 11 because of this. Because we added hydrogen and it's going to counterbalance that. Okay. Now, if it's going to go from 8, so if it's going to go from 8 to 11, that is an increase by, so that's going to be plus 3. Okay. So there was a plus 3 here. Now, remember, this is a ratio thing. Okay. So this is a 2 to 3 to 1 ratio, okay? Probably the important thing is to try and work out the nitrogen because it's the base of 1, but we can still do it with these other ones here. So it's a 2, 3, 1 ratio. So it went from, so some quantity, let's just go, went plus 3, okay? Now, here, these would go down minus x, minus 3x, and plus 2x. Now here, this is the plus 3, so the 2x represents that plus 3 in molarity, meaning x in this case is 3 over 2. So that means if we want to work out what these new molarities are going to be, we can just substitute x for 3 on 2 in both of them. So here, this would be minus 3 on 2, and this one here would be negative 9 over 2. Okay, so here, that's at 9. The nitrogen, so if I went 9 minus 3 on 2, that will be the new molarity. Now that should be a little bit below 8 because that's 1.5. So that should be 7.5, the molarity of nitrogen. And then the hydrogen is at 5, and we're going to go minus 9 over 2. So what's that going to be? So 5 minus 9 over 2. That's going to give you a half. So that's going to drop down all the way down to here, and that's what we should see after 15 seconds when it's re-established. So if we take a look at their answer as well, you're going to see that as well. Okay. We'll go here. We'll take a photo of just the next part of the graph, and they've done exactly what I predicted. Okay, let's go here. Alrighty. So the numbers we predicted are correct. Okay. That is at a half. Okay. This one is at 7.5, okay? 7.5. And this one here is at 11. So we got a half, 7.5, and 11. All correct, okay? That's how you answer question C, alright? Alright, let's take a look at question D now, okay? So let's go copy here. Alright, at 35 seconds. So this is pretty much 15 seconds after the 20 seconds. That's all that's saying. The temperature is increased. Okay, when equilibrium is re-established 30 seconds later, the concentration of nitrogen is 9.5 molarity. Okay, so this is to do with the delta H. Remember, it's exothermic, so pretty much when you add the reactants together, heat is going to be a product of that. Okay, so here, oh, okay, I always draw these guys incorrectly. That's okay. Negative. It doesn't really matter the amount here. So here, if I said, so if temperature increases, we're effectively adding energy. Now, if you want to think of exothermic, this is the best way to think about it. Rewrite your equation and just write energy on the right-hand side. Okay? So energy. So if I'm adding energy, I'm effectively increasing the products. So if I'm increasing the products and I apply Le Chatelier principle, it's going to indirectly decrease these two and increase these two. So if you increase the temperature, you should see an increase in the nitrogen and the hydrogen and a decrease in the ammonia, okay? Which is why the nitrogen went from, what was the old one? Nitrogen's at 7.5 molarity, and it goes to 9.5 molarity, okay? Okay, so now we've got to think of the ratio. So now we know the direction which all this is going. So here, we've got 7.5, 11, and a half, okay? Now, let's take a look at this. What was it? 2 or 3? Something like that? Yeah, 3. I keep drawing a H. It's meant to be an N. It's 3, yeah. Okay, so because of the temperature increase, that is going to be decreasing, those are going to be increasing. Now, that means that's going to get a quantity added. This is going to get 3 of that quantity added, and this is going to get minus 2 lots of that same quantity. So if the nitrogen's gone from 7.5 to 9.5, so if it's gone from 7.5 to 9.5, that's a 2 molarity increase, meaning X has to be 2 in this case here, because that's just the single quantity. So that means this is going to get plus 6, if that's plus 2, and this is going to get minus 4. So I'm predicting the new molarity. So for this one here, the ammonia will be, 11 minus 4? 6. That's it. So this will go from 11 to 6 molarity. It's going to go all the way down to here. This is going to increase, of course, to 9.5. And this is going to increase by a significant amount. This will go to 6.5. So that should go above here. Okay, and this is what we should see in the next part of our graph. So I'll just take a photo of the next part so you can see it. Alright, so let's go here. We can take a photo of pretty much most of it now, actually. That's good. Alright, let's go here. Alrighty. So here we can see if our numbers were correct. So here we have, that's about 6.5. That's, what do we say? Oh, did I do my math wrong? Oh yeah, 11 minus 4 is 7. Yeah, okay, that makes sense. Yep. And then that, nitrogen, what did we say? Yeah, 9.5. So we are correct. Aside from my little math area. 11 minus 4 gives you 7, not 6. Okay, or 6.5. Okay. Right, and that's how you answer that question there. Okay. Alrighty. At 65 seconds, an insert inert gas is added. Now, this, because it's not in our equilibrium system, it's actually not going to change anything at all. So the graph will actually continue along like this. Okay. So if I just take a photo or just copy the whole image now, because we finished this whole question, you can see it doesn't affect it at all, even at 65 seconds, because it's not a part of that equilibrium system. It's independent. Okay. Anyway, that's how you answer this question here. So a graphing question with equilibrium. If you have any questions at all in this video, leave a timestamp, and I'll try my best to answer it. But I'll see you in the next video.